question concerning the first assignment.
Yeah.
So basically for this question, yeah, this one, the C and question problem 3, which is basically if A equals 2 and 2 over 5 and B equals 5 over 2, how many solutions are there to the system? Okay. So we know that it's basically it's something over 11 minus AB.
Yeah.
So, and if you multiply A times B with those numbers that are given, you get 11. So it's 11 minus 11, which is 0, and so it's undefined.
Yep.
In that case, how many solutions will we have?
Either 0 or an infinity.
Infinity. Okay.
Yeah. So, and it depends on the rest of the constructors.
So basically, when it's undefined, it's either 0 solutions or infinite numbers.
Exactly. So this whole thing we're doing there, it's all valid, assuming that there is a single solution that we're trying to find. If there isn't, then at some point what you're doing is, oh, I'm on my way to finding the solution, and I'm dividing by 0, no problem. Yeah, there is a problem. So if there is a single solution, then you're not going to divide by 0. So the fact that there is either 0 or an infinity of solution is why you're getting at some point to divide by 0.
Okay, so in this case, there was, I guess, an infinity of solution.
Yeah, exactly.
Okay.
But so it's not all that bad. At least so it's not as bad as answering there's one. Because at least you know there is one is, so we would always like to have one solution. But yeah, so
Okay, yes. Perfect. Thank you.
Hi.
Next week semester, is it for all the materials we learned until today or until chapter 5?
Yeah, chapter 5.
Okay, so at the end of chapter 5.
Yeah, see, it's linear algebra. That's it.
Okay.
Yeah, that's more than enough.
Yeah.
Yes. Oh yeah. Just wanted to make sure yeah. So the exam was open on my computer. I didn't realize it. That's okay. All right, what time is it? Hello, everyone. I hope you had a nice break. You used it well to rest and learn and do whatever you like. So this is just a reminder of what we've seen last time. But just before starting, I want to say a few words about the midterm. So I wrote the midterm. It was more or less the same as last time, since I thought it would be nice. The average was 80% last time. But then I started freaking out for multiple reasons. First of all, last time is so I gave them the whole class for the midterm, but it was 3-hour class. So 3 hours to an hour and 15 minutes would be quite a jump. And I think it's not easy to answer all the questions, even if you have answerable questions. If you just have too many, it's just difficult. Second, it was online, and I have the feeling that not you, but some students cheat a lot online. So I don't know how you're going to do in person. So it might be lower than 80%. And finally, I just graded I just finished to find out the grades of my other class, which were a bit disappointing. So I'm like, no, let's at least have something that's not too bad. So I rewrote a bunch of questions and I removed some of the things. So hopefully it's doable. In my opinion, it's not too difficult, but of course, you have to not spend too long on each question. So you have to practice and practice and practice. So inverting things, computing determinants, solving stuff. Yeah, so I'm not going to go into too much detail because the previous version covered more or less everything. Now I really had to just drop some topics, so I'm not going to tell you what. So you have to study everything and hope for the best. But as a student, what I usually did is I thought exactly this. There's no way that the teacher can ask questions on all the topics. So if I want to have a 100% chance of learning everything that's on the exam, I should learn everything. But it's just so long that let me try and figure out the best probability to be at like 90–80% chance of finding on the questions that are going to be asked. So focus on the main points. So some side stuff, you never know. Maybe I'm going to throw you a curveball or something, but yeah, you should focus on the main things and be sure to be quick and to be clear in your answers. So they're all they're all little questions. Some of them take longer than others. So you have to compute an inverse at some point. I'm telling you, so you won't get away with without doing that. Otherwise, I'm not going to tell you about the rest. Yeah, so, and of course, if the class does super well, great. If you do super bad, then yeah, at some point I'm going to, I won't fail half of the class, so don't worry about it. Anyways, for most of you, I think it's material that you've already kind of seen, so shouldn't be too difficult. Yeah, go ahead.
What are the proofs, like on a test, if you have one to lift up like distributed law or commutative law, or you can just go right at that. So without mentioning the name.
Yeah, so everything is justified by something else. Even like if I do 1 + 1, this is because there is this thing that we call addition, which is an operation and blah blah blah. So of course I don't expect you to list everything, but if you come up at some point and there is like one step that is okay. Yeah, the way I see it is don't do two things at once. Don't skip over stuff. Even if because in your head, yeah, of course this goes away and blah, blah, blah. And so let me go to that. If I ask you justify, so be clear. Like if something is inside the parenthesis, then make it clear that you have an operation that you apply to the parenthesis, then apply it to each element inside it, and then to each element by itself.
Just as an example, like A, B, all transpose, right? Can I just write B transpose A transpose as opposed to saying, oh, this is a relation?
Yes, exactly. So you can do that. But what I wouldn't like is doing something like, yeah, it's good example. So if you have, say, AB transpose, and then, for instance, I told you that B is symmetric. Or A and B are symmetric, then I wouldn't like you to just, oh, that's BA, that's it.
Yeah.
So no, it's B transpose, A transpose, and the next step is it's BA because they're symmetric.
Yeah.
This kind of stuff, just for once, let's be a bit exhausted in the steps we take. But yeah, I'm not I'm not super tight into this because I could fail it. Even if I took my own exam and then gave this to a mathematician, I would fail it. So the point is not this. It's just to be a bit rigorous. All right, so back to what we were doing today. So this is just a reminder of what we said last time. So what we're doing basically is differentiation rules. So last iteration of this class was just telling you stuff. So I don't like to tell, I like to show. So let's show stuff instead. Yeah, so what we want is basically compute derivatives. But most of you or many of you know already this, so it's not going to be too difficult, but please, give your input if you have some ideas of what we must do. So good news. We don't have to take limits every time. We can use differentiation rules. Which we're going to show to you. Yeah, so that's the type. So function of one variable. Also, just before we start, reminder. So I'm going to use this notation f prime of x because I have some function of x. So what is that? So let's apply the definition. It's the limit when delta x goes to 0 of f of x plus delta x minus f of x over delta x. So just to remind ourselves what we're doing, this is the difference quotient. But when we take the limit of the difference quotient and make the difference vary or to a very, very tiny level, then it becomes the derivative. And we're going to just mostly apply this rule and derive the differentiation rules with them. So first, oh yeah, and we only care about functions of one variable. So no, yes, for now. Yeah, I dreamed of having more, but yeah. Okay, so constant function rule. So that's not too hard. So imagine I have y equals a constant c. So I take dy dx. So that's just, let's apply this. Yeah. So f of x plus delta x, it's c, minus f of x, it's c again. Since it's not a function of anything, so c doesn't change. So then what we get 0 all the time. So that's not too difficult. Now, constant. Oh yeah, and every time if I go too fast, just tell me. Sometimes I just get a tunnel vision. Factor function rule. So if I have something like y equals c times a function of x, and then I want to take the derivative with respect to x. So equals, so let's again apply the same definition. So if here I'm going to have, so this is my function. So I have c f of x plus delta x minus cf of x divided by delta x. And what do we know about the rules of derivatives with a constant term? We can just put them in front of it. So it's the limit of something with constant is the constant times the limit. So then we get f prime of x. So I didn't say what was f here. It applies for any sort of function. All I said is if I want to take the derivative and there's a constant in front of it, then it can be equal to the constant multiplied by the derivative, whatever the derivative is. Right. Now let's take x squared first. So what's the derivative of x squared? 2x, thank you. But let's discuss a bit why this is. So if I have y equals, oh, by the way, I think I'm not sharing my screen. Am I sharing my screen? Yeah. Sorry about that, people at home. That's the risk of not coming in person. I don't know what made me think about this, but okay. so y equals x squared. My pleasure. It was a very big effort of you to do that. All right, so let's apply our definition again. So dy dx. Something like this, but now I have, so my function is that parenthesis squared minus x squared divided by delta x. Okay, so what should I do next? What? Oh, yeah, sure. Okay, so what? Yeah, okay, so yes, exactly. So let's just do that. So I get x squared plus 2 delta x, 2x delta x plus delta x squared. And then what do I see? Well, first of all, the delta x cancels out with that one. This goes away. That goes away. And then I can just use the fact that if it's a limit of sum, so I can just, well, I can already divide it. Yeah, let's divide it already. So here, just get this. Here, this disappears. Yeah, I don't even really have to do anything with that. And what do I get? So this is an easy limit because there's nothing that goes to infinity or 0 in this, and this goes to 0, of course. So that's right. And so I wanted to take time to just discuss a bit why this is the case. Yeah, it seems obvious, but oh, sorry if you were still writing something. There it is. Okay, so let's just look at what this is. X plus delta x squared minus x squared. Well, we can just see graphically that this is a square. So what does that give us? And by the way, this would extend to other products, but because it's x times x, of course, but it's a very simple version of it. So let's be generous and have a large x. So what am I looking at? What happens? Well, I extend both dimensions of the square, basically. So let's have, here I have x, delta x, and delta x. And then this is minus. So, well, it's a bit small, so let's write minus. Oh, yeah, and then my x square is quite big. Didn't think it through. X. Delta x. delta x minus x squared. So what do I have left? Well, I have, let's have just this small tiny thing there to get a sense of what's going on. So if I take this minus this, well, I lose the big square. The big square is my starting point. What I care about is the change. So how is my square extending if I extend both sides by delta x? So I'm going to get 2 times delta x plus delta x squared. And then what do we see? So equals. And what do we see basically? It's that here delta x is going to 0. So if you compare the size of this with respect to the compared to that one, then these are these stay the same dimension. The x stays the same, but delta x is actually shrinking. So this little square here becomes negligible. So this is why I'm going to get but becomes delta x. So that's why all I care about is 2x delta x. So when I divide by delta x, I just get 2x. This is just a simple interpretation of what's going on. Power rule. So here I'm going to spare all of the demonstration, but it's somebody knows how you would show it for x to the n, whatever n is. So I get that dx equals to nx to the n minus 1. So some idea, some people know more about math and where I should go to prove such a thing. Yeah. So the goal is to, so you see what we did there. Here what we did is we just expanded this. So there's no trick. You just have to know what the expansion is, and for that you use the binomial rule. So you just use it, and all you see is that all the higher terms go away, and all you're left with is n of these terms there. So that's why with an exponent minus 1. So to show it. Left for the interested party. Yeah. So so if I have so x to the n equals to the sum of n. Oh yeah, we need some operator there for choosing. What is it? Yeah. So okay, there's a nice operator, but there's another way to write it. So n factorial divided by n minus, so yes, I equals 0. N minus I factorial times I factorial. Yeah, exactly. The thing is that I don't know where it is in my in my menu. Yeah, and this is of course x to the I. Just to verify. Please just give me the formula. Binomial theorem. Yeah, here it is. So x plus y. Yeah, so that's better. Okay, so but that's not at the exam. So can we copy this? Yeah. Okay. So I feel bad now that leaving stuff that I'm not sure about. So x plus y. Yeah, that's the thing. I forgot to have an addition. Yeah. Yeah, that's the thing. So y n minus y. Yeah, that's the thing. Okay, so this is it. And then if you just use exactly this, then you're going to see that all the higher order terms just become very, very small. And you're left with essentially this at the end. Yeah. With n terms of, but that's not like the exam, it's if you care about it. So an easy one, sum rule. So I have y equals to f of x plus y of x. So dy dx would be, let's again use the same template as before. So again, you just apply the rules and everything is going to go according to plan. Oops, oh, not y, but g of x, sorry. Plus g of x minus f of x. Yeah, just to be completely, that would be exactly our function, g of x. So this would be equal to, I just have to put the terms together. Here. And then this is a sum, so I can just state it at will. So I want to get this. I don't, there might be a less cumbersome way of showing it, but yeah, this works. So equals to f prime of x plus g prime of x. By the way, so this, what I'm showing to you, so there's a very little chance that I ask you to just show me something like that at the exam, but it's, why am I taking time? Well, because this is all application of limits anyways, and I'm going to ask you stuff about limits. So it's just a very good exercise to do them. Slightly less easy one. So once you see the trick, it's very easy, but figuring out what the trick is not so easy. So if I have same thing, but instead of an addition, I have a multiplication. X f of x g of x. So I'm going to get this thing. So this is multiply minus f of x g of x. And then what?
If that G are both continuous,
Yeah, but that's not the answer, right? Not f of oh, right, right. Yeah, but I don't want to take the limit of. Yeah, exactly. But I see your point. And by the way, so yeah, I'm going to discuss stuff later on. But yeah, so there's a trick. So here the problem is we have two terms that have just x inside them. So two functions with just x, and two functions with x plus delta x. And it looks like we're stuck. But so because what we want is do something similar to here, it's regroup them, put some stuff on one side, some stuff on the other side, but we're kind of stuck. So here is a trick. Yeah, trick that I think it works well. Again, I don't know if there's a better way, but so nobody has an idea what trick I should use. So think about it for like 30 seconds. It's not so easy, but if you think about it, it works. Yeah, math is all about creativity. It's art. Once you have it, it's all about imagination. Yeah, so I'm going to give you my trick. So the goal is, of course, to have just f of x plus delta x and f of x on one side, and the same thing for g of x, and having the rest disappear. Yeah, no. That doesn't work. So here's what you do. You add 0, but a special 0, which is this thing. So let's take f of x times g of x plus delta x. And then, of course, I want to add 0, so I'm going to subtract the same thing. And that little trick allows me to somehow do one thing first and then the other second. Here is what to get. So then I'm going to put, yeah, this here. These things. So all right, I'm allowed to do that. And here I'm just going to take in front the f of x. And the miracle, my two limits are appearing, my two derivatives are appearing before my eyes. Yeah, but I wouldn't expect you to see this right away. It's tricky if you don't know it. So let's just split these two. So I get this plus this. All right, so let's have g of x plus delta x in front of that thing, and f of x in front of that thing. And then we can just look at what we have. So here we have a limit of g of x plus delta x. So it looks like we are not out of trouble because here we have a delta x, but we know that at the limit, since delta x becomes very, very small and x stays the same size, then at some point delta x is going to disappear. So I can just keep x here. And here, yeah, I have the f of x, which doesn't change as I go to the limit. So I can just finally get this. This would be g of x, and I can just put it in. F of x can be. And then, so what do I get? This is f prime of x. And this is g prime. And this is the rule that we all know and love and dream about. All right. So, yeah, oh yeah, I remember one thing I wanted to say. So essentially what we sort of did here is said, so I'm going back to, but imagine that I have f of x and g of x here. I essentially said, let's deal with one dimension first, and then let's deal with the other dimension after. This dimension being starting with, say, f of x, and then g of x plus delta x in that dimension. But anyways, it didn't change anything because x plus delta x is like almost like x. So that was a way to divide the work that we had to do essentially. Okay. I hope you're still seeing this. Okay. So what did I do for quotient rule? Oh yeah, the quotient rule isn't all that difficult. So if I have y of x, y equals f of x divided by g of x. Is there some way I could deal with this animal there? Yeah, so that's the answer, right?
Oh, yeah.
But what I'm thinking is there some way to find out what it is if I don't know that? Yeah. So yeah, maybe. I had an easier way of dealing with it in my mind. With based on the yeah, exactly. Rewrite it as power rule. So we build on what we know already. So we know a bunch of things. We know product and we know power. So let's use both of them. So this is like if I had f of x times g of x minus 1. So x equals to oh yeah, why did I flip these? No, that's what I wanted here. F prime of x, I wanted this in front. It's just that the order I didn't like. That's how it's written. So I'm going to get so f prime of x times g of minus 1 plus f of x times, so let's write it this way, d this thing dx. Yeah.
Because you're finding the power rule of DMX.
Oh yeah, and I didn't say that, but no, but this I did I. No, yeah, I think you're right. I was sloppy. I defined it purely on X, not on. All right, I was going towards chain rule, but let's do it before that, just to be. That's all right. So if we are to be as rigorous as we can, so anyways, chain rule isn't all that difficult. So if I have y equals f of g of x, yeah. So this is yeah, this is fundamental. I should reintroduce it. So how should I deal with this? This one I could I could do it with the definition again, but there's an even easier way of doing it. So here's the way to be it. So let us introduce. What do I need? Yeah, new variable, which is just equal to what's inside there. All right, g of x. So what do I know? Well, I know that if I take the derivative with respect to x, so dx will be equal to just the derivative of g. So g prime of x. So then what I'm looking at for is this. So dy dx is going to be equal to, so dy dx times dv. So that's 1. It's always 1 regardless of how large it is, as long as it's not 0. And let's just flip these around. So then I can make this. So dy dv times dv dx. So it's going to be equal to, and oh yeah, so what is dy dv? Then it's just going to be f prime. So yeah, let me just say everything. So I have that x y equals f of, and then g of x, I have v. So then I am going to have that dy equals to f prime. Yeah. So what do I get? Times dv dx. So dv dx is g prime of x. And then I can also substitute v here, because v, that's just the value of something. And what is it? It's g of x. So I get rid of it. So yeah, and this trick is we did it without even using limits in our definitions. But if you were to try and do that with limits, that's possible. It's just that it's messy, but the same sort of trick would work, right? So chain rule done. So now let's continue with quotients. Yeah, so that's true that we're using so many rules and we stop thinking about them at some point. All right, so this works, and then plus this thing there. And what is this? So using the chain rule, so it's equal to so I get -1 g of x the minus 2 multiplied by g prime of x. So that's so just to show you what I did here, I applied it to the outside function, which is something to the minus 1. So it's the same as the product rule. So it's minus 1 times this something to the minus 2. I could just put this in parentheses. And then I had to multiply with the derivative of whatever is inside. This is what I do here. And then let's just correct terms. So we're going to divide by g of x. Yeah, exactly. So this is there. Here I had to the minus 1. So of course I have g of x times g of x to the minus 2. So that's, and then this went to the derivative. So, oh, is there something weird? Oh yeah, so the minus 1 can move here. So that's our product. All right, so yeah, many small steps. This was the chain rule, this was the product rule, and then just put everything together. That's also showing you something is I often say, well, if you want to prove something that looks similar to something else, usually you use what you did there and you just modify it. Yes, but you know, there are easier ways to prove different things. So I'm not saying you should always do that, because sometimes it might become quite complicated. All right, exponent function rule. So power rule is when I have x to the n. Now exponent function is something to the x. Y equals where a is some function. And how should I do that? Well, it dy dx equals a to dx. And I'm not telling you because it's at some point we have to stop the madness. So yes.
Does the base matter for this? Like, for example, say you want to connect to the power of that. Could I just use log of x? Like 10 to the power of log of x? Because we see that you're using ln, which is base c, right?
Yeah.
But like you can have other bases for the log of x.
Yeah, it's just that it's going to simplify. So if it's e here, then log of e is yeah, so it simplifies. But so 10 it wouldn't simplify, just add log of 10. So yeah, so this is actually it's even a way to define e is with defining it with limits. So I'm not telling you most, yeah. So just take this as a given and not question it. Learn it because this is the truth. I'm telling you. Wait, and remember that equals 1. So if I have e to the x, then it's just e to the x. Log function rule. So if I have y equals log a then y equals to 1 over x times natural logarithm of a. And again, I'm not discussing any of this stuff. Just take it as it is. But still, we had a good run, right? We could show most interesting things. Right. So that's what I had to tell you about the differentiation rules. Now you can just use them and life is going to be good and you don't have to use limits all the time. Just before we continue, any questions about what we've done so far? So again, I don't exclude entirely the possibility that I would ask you some of these things, but I don't expect to, just for the sheer fact that I don't want to tell you, oh, please learn this demonstration by heart. This doesn't make sense to me. I'm giving you some new problem that you haven't seen, but that looks like something you know, and you have to figure it out for yourself. So that's mostly what you're going to get at the exam. Function. Okay, so that's new stuff now. Inverse function. So, a lot of writing, I'm afraid. A function y f of x represent 1 to 1 mapping. So this means that you can write y equals f of x, but you can also write x equals f minus 1 of y. So both are, so there's a single value of x that corresponds to a single value of y all the time. Corresponds to a unique y. And y corresponds to a unique x. Also known as a bijection. Again, I'm not the kind of person to ask you vocabulary questions at the exam, but it's always good to know these things. Then the function has an inverse function which is x equals f. Yes, it's just what I told you. F minus 1 of y. So this is how we write it. And the note, of course, it's not the same thing as f of y minus 1. Because we don't even know if f can be applied to y anyways. So that's these are two completely different things. So taking the inverse function is really going back to where you started. Here is just f applies to x. That's all you have to know. So don't confuse both of them. So, oh yeah, so this is if f is strictly monadic. So now we're going to discuss what are monadic functions. So this is just some definitions there. I haven't introduced a lot of new stuff. Yeah, basically, if you want to find f minus 1, you just flip your x and y axes and you find it if it exists. All right, monotonic functions. Somebody knows what this is? It's a boring function, of course, because they're monotonic. So it's a function for which every time, so if x is a monotonic function, then for every x that's higher than some other x, then it has to correspond to a y that is higher than the other y. If it's strictly, then for x, which is larger than some other x, then y is strictly larger than the other y. So it's always growing, is what it is. Given a function f of x so it is strictly increasing if x1 greater than x2. Yeah, let's use x2 greater than x1. I don't know. 2 is greater than 1, so let's use this. Means that f of, I don't know if whether I should use a double arrow basically. Or imply. I'm not too I don't know all that much about math notation. So this is strictly increasing. So every time you have a x2 that's bigger than x1, then the function, its function would be bigger than the function of x1. And then, of course, strictly decreasing. No, if implies that this is smaller than this. Yeah. And if you have, if you want weakly, then you have smaller or equal. Yeah. Say that again. So you're saying about this?
Yeah.
Yeah, so it's both are both. Well, it depends which point you start. So if you're saying, so okay, just to be sure I understand what you're saying. What you're saying is I should write it this way. If x2 is smaller, then this is greater. But these are equivalent. Yeah. You had a question? This one then? Yeah, so the second one is decreasing. So this means implies, right? So if so let me, oh yeah, I have my nice pencil. So let me draw it. For real, actually, let's do it correctly so you have a record of it. So let's go back to this. Is that okay? So let me draw you a strictly increasing and strictly decreasing monotonic function. So you shouldn't be too stressed about this. It's really once I draw something, it should become. So here I have x and f of x. So this is monotonic strictly increasing because every time I have x2, here I have x1, then f of x2. Oops. Then I have greater than f of x. Here. Yeah, let me hide my okay. This then do I get so it's just you're ascending a mountain and there is no place in which you go back down. So this is monotonic. Strictly increasing. And then I can do monotonic strictly decreasing. And then, so neither monotonic nor increasing nor decreasing would be something with valleys and canyons and stuff. Okay, so it's really nothing to be scared of. It's just a definition of properties of function. All right. So, and then, yeah. So let me just discuss a bit more. So what this means is, what it means to have an inverse function is to flip f of x and x And then you still have a function because there's a bijection. So there's a single value of x that corresponds to f of x, or x of y and y to x. So then you can flip them around and you still have functions. So that's why what this is. And the other would work too. It wouldn't work in that case because you would start with a function but end up with not a function. So that these are concepts that we've seen before. Right. So if f prime of x is greater than 0, so think with derivatives. So how do you know whether or not a function f is or isn't monotonic? Then you just compute the derivative. If you can compute it, maybe you cannot compute it. Still, it might be monotonic, but non-differentiable. But if you can compute the derivative, then you will get that f prime of x is greater than 0 for all x. Implies that f of x is strictly increasing. Or we can say upward sloping. And then if the derivative is negative for all x, so that implies that f of x is strictly decreasing. So downward sloping. Again, so just if you take the derivative anywhere, then here the derivative is always positive. The slope is always positive. Here the slope is always negative. And here sometimes you have a positive, sometimes you have a negative slope.
What about heteroscedasticity?
So heteroscedasticity?
Yeah, it's using statistics.
Yeah, the variance isn't uniform in your data set.
Yeah, with that, it's not monotonic in the sense like strictly like there is kind of upward.
Yeah, okay, so if it's what I would say is if I have well, it depends. So you can have heteroscedasticity that's not monotonic.
Yeah.
So okay. So have some of you done statistics before or econometrics? No? Yes, a bit. So you know what heteroscedasticity is? Yeah, so if you have, say, a set of points, and they are very close together at some point, and then more spread out as you go, then you would say that, okay, maybe heteroscedasticity is monotonically increasing with x, for instance. But then again, also, it depends how I model it. So it's all probabilistic. So here, this is really deterministic. This is just, I gave you some function. These are their properties. So the joy of statistics. Yeah, all right. Okay. So, oh yeah, cool. So now to find it. So to find. So these are all the conditions that you can check or you want to check before you want to try and find the inverse. So to find the inverse function, you change f of x invert and solve. That's it. Not too or rather sorry for x. Yes. So just to give you an example, so if I have f of x equals 2x, so I can just have y equals 2x, and then I solve for x, so I find that x equals to y over 2, and this would be x equal, so this would be um, yes, yeah, so okay, yeah, exactly, so f inverse, but yeah, that would be y. Because I don't want to say that it's the same variable, but it's the inverse of that one.
The range, well, in this case, it's between the different, so sometimes it's the range that the names can change.
Yes, exactly. So I could say I limit myself to this section of the function, and in that section, that's a bijection. So let's flip and you know, so on the x-axis you might have a certain range, on the y-axis a totally different range, and all these have to flip. The image and the domain have to flip. Yeah. Okay. So what do I have? Okay, let's just finish with rules of derivatives. So that's the last one. And then we can call it a day. And then I have, I introduce multiple variables. So last rule, rules of different derivatives. Inverse function rule. If I have dx dy, it can be equal to 1 over dy dx. So the derivative of the inverse function is the reciprocal of the original function. If is strictly increasing or decreasing, then so must be f minus 1. Okay, so this is a neat trick. A neat trick. Why? So one case, I'm not going to just to do it. Maybe I do it later. But if you compute elasticities, so oftentimes when you look at what happens with demand elasticity and what you should do if you want to maximize your revenue, for instance, or if you want to look at the degree of competition in market, then you always go back and forth between the demand and the inverse demand, and the elasticity is defined in terms of demand. So you have to be able to fit them. And that's why we're always able to say we have X and P or P and X, you can always do these things because we assume that the demand is a monotonically negative function. So that's just a small link with economics at the end.